We're going to be learning a technique of integration called integration by substitution in section 5.5 today. And integration by substitution is your most important technique of integration. If you're going on into Calc 2 and Calc 3, substitution is going to be with you for a very long time to come. In fact, it's so important that we're going to park here in this class for a couple of class days and a couple sets of videos just to make sure you get the technique down. So substitution is kind of our way of doing the chain rule backwards when we're finding antiderivatives. So let's remember the chain rule. When we're taking the derivative of something that has an inside function, I'm going to take something pretty simple. Let's take the sine of 3x. So we know when we take that derivative, we take the derivative of the outside function. Derivative of sine is cosine. Leaving the inside function alone, then we multiply by the derivative of that inside function. Derivative of 3x is 3. So this gives us that the derivative of sine 3x is 3 cosine 3x. So the easy antiderivative here would be if I had the antiderivative of 3 cosine 3x. Because I just took the derivative, I know that the antiderivative of 3 cosine 3x is going to be the sine 3x that I started with. So we would say this would be sine 3x. It's an indefinite integral, so I would throw a plus c on there. But what if our integral doesn't come pre-rigged with that 3 from the chain rule? So what if I just give you the integral of cosine 3x? I really wish that that 3 was there so it could be the derivative of the inside function for me. So substitution is going to give us a methodical way to figure out how to do this every time. But the idea behind it is that I wish that that 3 was there for the derivative of the inside function. So I'm going to put it in my integral. So I'm going to do a little bit of wishful thinking with my green pen. I'm going to say, I wish there was a 3 multiplying times that cosine 3x. Now, we know we can't just go around multiplying things by 3 because we don't like them. Otherwise, I can multiply my paycheck by 3. So I can only multiply by 3 if I sort of compensate for that so that I haven't really changed the integral that I've got. So what I'm going to do is I'm going to multiply by a 1/3 as well. And since constants can move in and out of the integral, I'm going to put the 1/3 on the outside. All right. So I know that the integral of 3 cosine 3x is my sine 3x, but I'm going to have that 1/3 hanging out outside on the front, so I didn't really change the integral. So this is going to end up being 1/3, and then I know the antiderivative here is going to be that sine 3x. And then, as always, r plus c. And so that 1/3 is hanging out there so that when I take the derivative of sine 3x and it becomes cosine 3x times 3, the 1/3 is ready there to cancel out the 3 and just give me that plain old cosine 3x. If you didn't really love what I did with the green pen on the last slide, you'll be relieved to know that substitution is eventually going to be a very straightforward methodical process. We just need to get our brains wrapped around it. So I'm going to rework the same example for you, and I'm going to show you the way we do it using U substitution. So I'm going to write my integral cosine 3x dx. What we're going to do with U substitution is to make up a new variable u and define it to be the inside function in my integral, and identify the inside function the same way you do with the chain rule, just which function is on the inside. So I'm going to define u to be equal to that inside function 3x. Then I'm going to take the derivative of u and I'm going to write it down with Leibniz notation. And so this is du dx. Take the derivative of 3x, that's just 3. And I use Leibniz notation, so I make this dx thing show up, which is really important to our integral. Now I'm going to do something weird. I'm going to multiply both sides by dx. And I'll show you why we want this in just a second. So this gives me that du is equal to 3 dx. And our goal is going to be to use the u equals 3x and du equals 3 dx to rewrite this integral in terms of u and du. So u is equal to 3x. So I'm going to replace 3x with a u. Now I would like to be able to change that dx into a du, but dx and du are not exactly the same thing. In order to change dx into du, there has to be a 3 on my dx, right? 3 dx is equal to du. So I'm going to introduce my 3 into my integral. I'm going to put a 3 in here because I need that to pair up with the dx to make me a du. So 3 and the dx together are going to be my du. But I can't just put the 3 in there. I have to compensate on the outside with a 1/3. So I'm going to put the 1/3 out here. All right, so let me write down everything I've got here. I've got this 1/3 hanging off on the outside. I've got the integral. The 3 and the dx are going to get stuck together at the end of the integral as a du. And then I've got cosine u at the front. So we're going to have cosine u du. So everything that was an x is now in terms of a u, and I've compensated for everything I've changed in the integral. And what this does is it makes the integral look easier than it did at the start. Integral of cosine u du, I know that antiderivative is just sine. So the 1/3 is going to go along for the ride. Sine, make sure we use the same variable, u plus c. And at the very end, we remember that u was a figment of my imagination, and we're going to plug back in for u. U is equal to 3x. So this is 1/3 sine 3x plus c, which is the same answer that I got when I was just kind of thinking about the derivative of the inside function. If this feels like a whole lot of work to you, I promise this is going to be more and more necessary as these integrands get more and more complicated. So like I said, we are going to hang out in section 5.5 for a long time, and all we're going to do is examples of u substitution. But I wanted to take a second to write this down in a procedure for you so you can have it to look at. To integrate by substitution, you're going to let u equal the inside function. Then you're going to rewrite the integral in terms of u and du. That's really where all the hard work is. And then you're going to evaluate the integral and change back to your original variable. Our u substitution technique tells us to let u equal the inside function. So we're going to say what function is on the inside of another one here? Inside would be x squared minus 4. So I'm going to let u equal x squared minus 4. Last time I wrote this down, I wrote Leibniz notation. I said, let's take the derivative du dx, and then the derivative on the right would be 2x. And then I multiplied both sides by the dx. So multiplied by dx and multiplied by dx to solve for du. Usually we're going to skip ahead to this step where we just say du is equal to 2x dx. You're always going to want to move that dx over to the right-hand side. Then our goal is to rewrite this integral in terms of u and du instead of x and dx. So the x squared minus 4 that I picked for my u is here. And then we want to be able to turn that dx into a du. In order to have a du, I need a 2x dx. Well, so far so good. I've got a dx and I've got an x, but I need a 2. So I'm going to introduce a 2 to my integral. I'm going to compensate for that by multiplying by 1/2 on the outside. So 1/2. And that's just so that I don't change the integral. And now I have a dx, I have a 2x dx together make a du. So let's see what we have left. I've got the integral, well, 1/2 times the integral. I've got u to the 10th, and everything else in that integral, the 2x and the dx, gets sucked into that du. And this is the goal right here. U to the 10th du is an extremely easy integral to evaluate. It looks much simpler than that x parentheses stuff to the 10th that we started off with. Find our antiderivative. The 1/2 goes along for the ride. U to the 10th, we know we just add 1 to the exponent, divide by the new exponent. Add our plus c. Let's multiply those denominators to get a 22. And let's plug back in our u. So we're going to say instead of u to the 11th, it's x squared minus 4 to the 11th. And then on the bottom, we'll have a 22 plus c. Like I said, we're going to do a lot more examples with substitution. So if it hasn't really sunk in yet, hang in there. It's going to make sense eventually, I promise. Before I do some more examples, I want to mention one important thing about this integral. If that x outside the parentheses had not been there, this integral would have been impossible by doing u substitution. Let me show you why. So my integral, if it had just been x squared minus 4th to the 10th dx, and I tried to do that same u substitution in blue above, I would have gone to my integral and said, okay, this is going to be my u, and then I'm going to try to turn that dx into a du. And I would say, I need a 2x dx, so I'd have to put a 2x in here. The trouble is, I've been sort of nonchalantly just pulling that 1/2 or that 1/3 or whatever that compensation is out front. And I've been able to do that because constants can move in and out of integral signs. Constants can do that, x's cannot. So you can't put an x in an integral and then compensate with it on the outside 1/2x. You can't do that, it just doesn't work. So the only thing we can fix by u substitution when we're changing from a dx to a du are things involving constants, not variables. So if you were given this integral, x squared minus 4 to the 10th dx, if you wanted to find that antiderivative, you would be stuck foiling out x squared minus 4 10 times all day before you could find this antiderivative.